Yeah, thanks for the introduction. So welcome everybody to my talk about telemetric orthodontic brackets. Yeah, first I want to start with the motivation. Why do we need these smart brackets in orthodontics? The forces and moments applied to the teeth are of crucial importance for orthodontic itself. So everybody of you, or many of you, know these apertures you get into the mouth, and these single brackets aligned with a wire acting on the forces, or applying forces and moment to the teeth in order to correct misalignments of the teeth. And nowadays, the orthodontics adjust these forces just by feedback of the patient, so there is no actual quantitative feedback for them. And since these forces are in the Newton and below Newton range, there is a critical force which is exceeded. It can already damage the tissue and can lead to root absorption. So the goal of this project is to integrate a complete sensor system capable of measuring all forces and moments in 6 degrees of freedom, meaning Fx, Fy, Fz, Mx, My, Mz, and completely integrate that into the bracket itself. The available area we have here is one of the critical requirements for the system. The available area is only 2 times 2.5 square millimeters, really tiny area. And the system, of course, needs to be operated wirelessly. You don't want to have tons of wires in your mouth, so the wireless operation over a distance of at least 1.6 millimeters is necessary to make it applicable for therapeutic applications. The forces are in the range of plus minus 3 Newton and plus minus 3 Newton centimeter approximately, which are interesting for this orthodontic application. So the idea is, we use a CMOS integrated chip of the same size as the bracket, connected to a microcoil, which is then being powered over an inductive link. And this principle is just the same principle as any RFID tag we have commonly. So we put the energy in, put the inductive link, and by some modulation on the chip, you get the data back. So this is planned to be then adhesively adjusted or integrated into the bracket itself. And that's actually the idea. And the realization I'm coming to now is the CMOS chip itself. It's a standard CMOS process by the company X-Fab in a 350 nanometers technology. The chip size is just the size of the bracket, 2 times 2.5 millimeters with a thickness of 0.3 millimeters. And indicated on the right, you can see the stress-resistant elements. These are realized by, in total, 32 piezoresistive field effect transistors, which are basically sensitive to the normal stress, to the in-plane normal stress of the sensor. So these 32 sensors are located on the chip on several positions, getting a stress profile over the whole chip. And it additionally the chip is equipped with a telemetric interface, handling the RF incoming power from the coil at the standard ISM band frequency of 13.56 megahertz, which is a standard frequency in RFID applications, and free for medical applications as well. And here's some more data about the chip. Each stress-sensitive element, each sensor of these, indicated here on the right, has a stress sensitivity of 900 microvolts per megapascal. The resolution of each of these sensors is 20.5 approximately kilopascal. The data rate at which the chip is transmitting the data is 27 kilobits per second. And this, for all 32 sensors distributed to the chip, results in a total readout time of about 1/6 of a second. So this is quite fast enough for this static application in the mouth. For some dynamic other applications, maybe a little lower. And the total power consumption, we propose we need to deliver wirelessly through the inductive link is 17 milliwatts. This was one of the major challenges in that project actually. And how to equip that chip now with a microcoil acting as the receiver for power. We therefore came up with this process in our clean room at Impact University of Freiburg. It's a custom clean room process which made us capable of squeezing quite a lot of current on that tiny area. And it starts with the metallization of a glass substrate of titanium and gold, after which we structure the gold lines in the shape of the coil, which is then being the seed layer for the coil for later electroplating. We do the thick resist lithography, the blue resist here. Do the electroplating of copper and gold into that resist. And then after stripping the resist, you can notice that we are in a quite favorable situation. We just need to remove the titanium underneath, and titanium can be removed completely selectively with wet etching here. That's HF etching. And then after that, after we wet etch the seed layer, meaning removing all the shortcuts between the coil lines, we can encapsulate this with a SU8 epoxy and open the pads for the coil graphically. And the results for that, you can get here you can get up to like 300 coils per wafer. This is a 4-inch wafer here, and on that available area we can have for the brackets, 2 times 2.5 millimeters, we can get up to 35 grams. And this results actually in 5 microns of line width, of a minimal track width, and the minimal spacing between we could achieve with 10 micrometers. The plating height is about 22 micrometers distributed over the wafer, and that was basically the maximum of aspect ratio we could achieve. So the goal, of course, was here to plate them as high as possible to reduce the line resistance and therefore to reduce the losses. And after encapsulating these coils here, they can be then connected to the CMOS chip via flip-chip bonding. What we actually use is hot pump assisted flip-chip bonding. So we first provide a gold pump on the pads, and then actually flip-chip bond the coil on the CMOS chip. Do a underfill with a biocompatible epoxy. This is called Epotec, and with the same epoxy, you can then just attach the whole chip assembly adhesively to the bracket. Here on the lower right side, you can see the whole assembly attached adhesively together with a ceramic bracket. So yes, so then the chip side is finished, and how do we read that out? That was also quite a crucial thing. How do we optimize it or maximize it? Yeah, basically this is already equipped with an antenna, but for our purposes it was way too large, so we need to find the correct antenna, and I'm going to show you in the next few slides how we found it. So the custom antenna we optimized. We just so in the first order approximation, there's always optimal antenna diameter for every distance of the reader unit. So if you have a look at the magnetic field of a conductor loop, you can get this equation. This is directly derived from Biot-Savart's law, that when you are at a fixed distance away from a loop and you change the size of the loop, you get this curve. And each of these curves for several distances of proportionally decay when you're far away from the conductor loop. Each of these curves have a peak, and this peak is actually the optimal antenna radius. And this is also applied in RFID technologies. And therefore, for a reasonable distance we can achieve, in this case, the optimal antenna diameter of 3.5 millimeters was calculated for actually a distance of 2.5 millimeters. This is kind of the chip dimensions. So you can estimate the first order approximation. You can estimate the maximum transmission distance to be almost like as large as the antenna diameter itself. So in this case, we found this optimal diameter for the coil. And the next thing was, we want actually a coil with a high quality factor in order to get the high power transmission and less loss. So what we did, we have this manufactured at a company in Germany with about 6 to 20 turns turns for the coils, and we had a set of coils, and we actually selected the one with the highest quality factor we could get to maximize the transmittable power. And this results in the increased transmission distance, which was the actual success of everything, because now with this tuned and optimized antenna and with the corresponding commercial IC, we were first time capable of reading out the chip over a distance more than the thickness of the bracket. And in this picture, you can see that it's not only a little bit more, it's quite a lot more. So the bracket itself is 1.6 millimeters, and we can read out almost twice the bracket. So this is the readout experiment. You at the maximum distance, And on the right and lower side, you can see the signal which is being read out at the primary side, at the coil, and with a self-program and decoding mechanism on the microcontroller, also on the readout board, we can decode that signal and decode it and transfer it serially to a graphical user interface or a PC. So in the last step, we need to calibrate that system. How do we get the actual forces and moments in the 6 degrees of freedom? So what we did, we had a mechanical setup with a load arm which applies forces and moments onto the arc wire, which is then connected to the bracket. And on the lower hand, you can see the reference sensor, which is then measuring the actual forces and moments. And with a so-called inverse calibration method, we can get the projection from the 32 sensor values to the 6 values of loads. Actually, this is the calibration matrix A we're looking for, connecting these two quantities. After you have then calculated this calibration matrix, you can apply it to a new set of loads. You can do, again, let's say some forces moment, apply it to it, and can then compare what you get in order to comparison to what you apply. And ideally, this would be linear curves, of course, so the unit slope, and the error is indicated in the lower right for each force and moment, and are quite below the values of the interesting range of the sensor system. So I'd like to conclude the talk. We demonstrated the CMOS stress sensor chip with 6 degree of freedom functionality, extremely miniaturized, and we were able to wirelessly drive that and get the data out, including also we fabricated the microcoils in order to get that transmission working. I showed the flip chip assembly, the custom antenna designs in order to optimize the transmission distance, and in the end I've shown the mechanical calibration and the validation of the data. So hopefully this girl now will have the brackets less time than before, and hopefully the smart brackets will help her. And in the end I would thank the Hahn-Schickert Institute for providing the chips and the Brainlings Brain Tools Excellence Cluster for funding. And also I'd like to thank Professor Bernd Lapatki, who's the orthodontist working with us together, and of course Professor Oliver Paul and my group, the Intex Material Laboratory in Freiburg. So thanks everybody for the attention.